Alright, so this short tutorial will address some of the murky points related to energy and that energy balance of the Earth. So the first thing that I'd like to address is what the difference is between latent heat flux and sensible heat flux. And the second thing is if the Earth releases more energy than it emits, then why aren't we experiencing global cooling? Why are we talking about global warming? Well, the first thing we have to do is go back to this very lovely figure, which is basically demonstrating the Earth's energy balance. So if we look at the annual energy balance for the Earth's surface, including the gains that we get from solar radiation and gains and losses due to the emission of infrared radiation, this latent heat flux, and sensible heat flux. The numbers are gains and losses of energy, and in this figure they're given as percentages of the average annual incoming solar radiation at the top of the Earth's atmosphere, which is estimated to be about 342 watts per meter squared. Okay. Now, once this incoming solar radiation enters the atmosphere, it has to be distributed or redistributed in some ways. This is done through two mechanisms, ocean currents and wind currents. These are heat movers. So we know that energy is stored as heat. So energy is stored in the form of latent heat in the atmosphere. Now in surface waters of the ocean, it is stored as sensible heat. And I'll explain a little bit more about what each of those terms means in a second. So just remember for now that atmospheric and oceanic circulations both share this task of redistributing this heat that comes in the form of solar radiation. Now, if we think back to latitude and the tilt of the Earth, on the whole, heat has to be moved from the tropics, where the sun is closer to being overhead at noon, and so in other words, it's much more direct sunlight, so much more of the solar radiation is hitting the tropics. So unless some of that radiation is redistributed to other parts of the planet, there would be a huge deficit. So the tropics would be much warmer than they already are. And the much higher latitudes, for example, up here in Minnesota, we would actually be much cooler if we didn't have these ocean and wind currents doing their jobs of redistributing heat. So, sorry for the fuzziness of this picture. So, as mentioned, this redistribution of heat or of energy across the Earth's surface is accomplished through two ways, the sensible heat flux and latent heat flux. So we can think of sensible heat as the energy associated with the temperature of a body. It is greater in a warm body than in a cold one. So when warm water that is heated in the tropics and cooled in high latitudes, that brings that sensible heat poleward, or in other words, just toward the poles. Now when warm winds carry sensible heat from one place to another as well. So when picking up water along the way, so when winds are blowing, they pick up water, for example, from the sea surface, the winds can also change some of this sensible heat into latent heat. This latent heat is the energy associated with a changing of a phase of a substance. For example, when something changes from a gas state to a fluid state, or from a fluid to a solid, and so forth. The enormous amounts of latent heat involved in evaporation and precipitation of water makes the hydrologic cycle a huge player in the operation of climate, which we'll get to in later chapters. So in this diagram that illustrates this latent heat flux, that latent heat flux is just simply that global movement of latent heat energy through circulations of air and water. And again, think of changing states. This illustrates how that atmospheric circulation moves latent heat energy horizontally, so from the tropics to cooler locations where it's condensed as rain or deposited as snow, releasing heat energy stored within it. Okay? All right, so then if we go backwards a little bit and go back to this figure, the one thing I want you to really understand about this figure is when we're talking about latent heat flux and sensitive heat flux and so forth, this is just showing the losses, so the consequence of this redistribution. There is going to be energy loss when as energy changes phases, whether it's from evaporation, there's going to be some heat loss, right? So it's just simply a consequence. And this is just sort of the accounting for that when it comes to incoming solar radiation. Now, as for the question as to why are we not experiencing global cooling instead of global warming, because we know that the Earth's surface actually receives more energy than it receives by direct solar radiation. So, why is that? Why are we still warming up? Well, the answer to that is in the greenhouse gases, which I know many of you, if not all of you, have learned about these at some point. So these greenhouse gases. So what are greenhouse gases? Well, greenhouse gases include probably most dominantly would include carbon dioxide, as well as methane and nitrous oxide, and even water vapor or aerosols that are suspended in the atmosphere. These greenhouse gases have the ability to capture some of this energy or heat that's re-radiated from the surface in the form of outgoing long-wave radiation. It captures some of that and re-radiates it back toward the Earth, thus giving us a warming effect. So this back radiation. Now, why we're experiencing global warming, which is a phrase I really try to not use very often because I think it has some negative connotations, but why we're experiencing global warming or climate change is because of the composition of these greenhouse gases in terms of density, as well as the types of gases that are present. So the more greenhouse gases that we have, the more of this back radiation we can experience, or the Earth will experience, thus having a warming effect and not a cooling effect, as we might otherwise have if we did just simply go off the fact that the Earth is receiving more energy than it's releasing more energy than it's actually receiving. So hopefully that makes a little bit more sense. I don't expect you to know this figure inside and out. I would just hope that you can understand sort of the basic concepts, the basic accounting for what happens to this incoming solar radiation once it hits our atmosphere. All right, so hopefully this cleared things up for you. As always, if you have more questions, send me an email or raise your hand in class.